We are now going to begin building the systems that will run our simulation. We will start with the map system, which will manage the world map. Let's first create a new folder to hold all of these systems, and then we will define a base class which they will all inherit from. We will call this base class Simulation System. The first key distinction to point out is that these systems will not be Unity components that inherit from monobehavior. We want to keep the simulation as separated from the Unity rendering as we can. We will delete all of these Unity methods and then place this class in the root namespace. This base class will contain a number of virtual methods that will be common to all of our simulation systems. The tick method is going to have the same signature as the event handler we defined for the onTick event in our simulation manager. We are making this method protected because it does not need to be public when it is being used as an event subscriber. Essentially, the class will be notified of the event and then it will call its own method in response. But the init and quit methods will be public because the simulation manager will call them directly. We are making these methods virtual in case a system doesn't need to do any specific initialization or cleanup. This way we don't have to override them in the inherited class. Now that we have the base class defined, we can create our first simulation system. This will be the map system. We will place this system into the root namespace and then we will give it the simulation system base class. We can now begin to override the base class methods. Since the methods are empty, it is not necessary to include a call to the base class method. We are going to include a private setup events method in this system where we can subscribe to the onTick event we set up in the last video. We will subscribe by supplying the event handler with the tick method we defined in the base class. To subscribe to an event handler, we can use the += operator to add our method to the event's list of methods to call. Notice our tick method takes an onTick_args argument, just like the event handler we defined in the simulation manager. We can then use the quit method of our system to unregister our tick method from the onTick event handler. This way, if we eventually change to a different scene like a settings menu, we can stop listening for the event. Now our map system's tick method will be called every time the simulation manager fires an onTick event. Let's test this to see the tick event in action. We will place a debug call into our map system's tick method. We should see the tick value every time the tick event fires. Now we need to go into our simulation manager and create an instance of our map system for it to manage. We will define this instance as an auto property with a public getter and a private setter, just like the instance variable above it. In the awake method, we will instantiate the map system, and then we will introduce the Unity start method where we will initialize our simulation systems. Let's also introduce the Unity onDisable method so that we have a place to call the quit methods for our systems. That's all we need to do to hook up our map system. Remember, the tick method will be called when the simulation manager fires the onTick event. This way, our simulation systems will only update when a simulation tick occurs, and they will not be updated each frame like a Unity component. This helps us separate the simulation logic from the rendering logic. Now we can run the application and see if we get the debug messages every time a tick event occurs. There they are. To get a better sense of what's going on, let's change the tick duration value we set in the simulation info script. We will set it to 1.2 seconds. Now, our tick events should fire only every 1.2 seconds, and the messages should appear much slower in the console. It looks like everything is working correctly. Let's set the tick duration back to 0.2 seconds, and now we can move on to building the world map. Let's start by creating a folder that will hold all the scripts that are associated with the map. We will define 3 enums that will represent the different types of tiles for the layers of our tile map. First, let's create a script called groundType. Let's open that script, place it into the root namespace, and then change it into an enum. We will include a none value to represent a cell that does not have any ground tile defined. Then we will include 2 types of ground tile to begin with. These match up with the 2 floor tiles we imported earlier. We will now follow this exact same pattern with the other 2 layers of our tile map. Let's copy the ground type enum we just created, and we will then create a structure type that represents things like walls that will sit on top of the ground layer. Let's also create the script for the overlay type, which will sit above the other 2 layers and allow us to do things like highlight a tile with a sprite. Now let's copy the structure type and move on to the overlay type. Here you can see an example of the overlay tiles we will use to select a tile. We now have all the tile map types we will need. Let's move on to creating a class that represents each cell of our tile map. Just like the other classes associated with the simulation logic, this class will not inherit from monobehavior. It'll simply be an abstract representation of a cell in our map. Later, we will translate this into something that Unity can render, but we want it to exist separate from rendering concerns in order to emphasize the distinction between our model and our view. The cell class will essentially be a container for data about a cell. Each cell will have a unique ID that defines its position on the map. It will also have a Boolean value that determines whether it is a solid cell that an entity will not be able to walk through. Even though the ID will determine the cell's position on the map, for convenience, we will also store the cell's position as a 2D vector. We are going to use the Unity mathematics library in our simulation, because it has a very nice representation of vectors that aligns well with standard naming practices in shaders and with the basic data types like int and float. Finally, each cell will contain a reference to all 3 of the tile map layer types we just created. This way, each cell can have a ground tile, a structure tile, and an overlay tile. Now we can actually define the world map class. This class will also essentially be a container for data about our world map. It will make use of the cell class we just defined. We will define a few properties that give us useful information about the size of our map. The first property will be called size, and it will represent the distance from the origin of the map out to one of its edges. Next, we'll define a property called width, which will represent the entire length from one end of the map to the other end. This will be twice the size plus 1 to include the origin point in the middle of the map. Finally, we will define a property called area, which will represent the total number of cells in the entire map. This will simply be the width of the map squared. We also need a list of all the cells in our map. We will define a constructor for our world map that takes in the size. It will then initialize the list of cells using this size as the capacity for the list because the number of cells in the map will not change. Notice the width and area are properties defined in terms of the size, so we do not have to initialize those properties. Let's also turn the size variable into an actual property and make it setter private like we've been doing with the other properties. That's everything we need to get started building the world map in our map system. We can now use the map system to set up our world map within the simulation. Later, we will introduce a Unity component that will translate this map into something that can be rendered to the screen. Let's start by adding a generateWorldMap method to our map system that we will call in the init method after we set up the events. We will now include a private world map instance variable, and then instantiate this variable in the generate world map method. We are also going to introduce another info class to store general data about the world map like the size. We'll call this class mapInfo and place it into our info folder. Let's open this class and set it up just like our simulation info class. It'll be a static class with static members. We will introduce one static int variable that holds the world map size. We will start with a map size of 24 tiles. Remember, this is the distance from the center of the map to the edge. Now we can return to the map system and use this variable while initializing our world map. We will now iterate over the total number of cells our map will need, and create a new cell for each position. Remember, the total number of cells will be equal to the area property for our world map. We will assign the iteration variable to the ID property for each cell. And we'll start out with each cell having a solid property of false. But we need to introduce a helper method in order to calculate the grid position for each cell based on its ID. We will call this method ID2Position. It will take in the ID value as an int and then return an int2 vector representing the position that matches up with that ID. Converting a cell's index to its 2D position in a grid is a well-known algorithm that uses the width of the grid in order to recover the two coordinates from a single index value. In our case, the width of our grid is stored as a property in our world map. The algorithm relies on using the normal division operator and the modulo operator, which returns the remainder of a division operation. The modulo operator is represented by the percentage sign in most programming languages. The x position for each cell will be the remainder after we divide the ID by the width of the map, except in our case we want our simulation map to have its origin at the center of the world, rather than at the top left. In order to account for this, we will subtract the size of the map, which is equal to half the width of the map. This will move the x values over so that an x value of 0 is now at the center of our world. The y position for each cell is found by simply dividing the ID by the width of the map, because each time we increase the y position by 1, we have gone through the width of the map one time. If we're on the 5th row of the map, then we have counted up to the width of the map 5 times to get there. And again, we will subtract the size property to ensure that a y value of 0 on our map is in the center and not in the corner. It might be worthwhile to return to this algorithm after we have the map rendering on screen in order to better understand it. We can now use this method to calculate the position vector for each of our cells. To complete the instantiation of our cells, we will define them all to have the floor 1 ground type and none for their structure type and overlay type. Now we will add each cell into the list of cells in our world map. This completes the generation of our world map. Remember, we want the simulation to exist entirely separately from how it is rendered. We want to be able to run the simulation without worrying how it is going to be displayed. We have not introduced any Unity game objects or sprite logic into the world map at all. In the next video, we will begin setting up the rendering resources we need to actually display the map on screen.